What's up, guys? I'm sorry I haven't been posting any videos lately. You see, I've been working this new internship with the Los Angeles Dodgers, and it's been taking up most of my time as of this week and last week. I actually did release a video last week regarding the Battle of Agincourt, but it was too long for the YouTube moderation system, so I wasn't able to get that out to you guys. I'm gonna work on getting that out as soon as possible. Um. Anyway, so today we're going to be doing a review on this book called Algebraic Topology by Alan Hatcher. This is like a math textbook. This is actually a very special episode. We're going to be doing a math review. So, start off, this book is one of the most widely used modern textbooks in its field. The book develops the central idea of algebraic topology, translating geometric and topological spaces into algebraic objects like groups, rings, and other various complexes, so their structure can be studied more systematically. The book is organized around four major themes. So first is the fundamental group in covering spaces. The first section introduces the fundamental group, denoted pi log 1 times x, which measures the different kinds of loops in space. So the core idea is that two loops are considered equivalent if one can continuously deform into the other, and the collection of these equivalent classes forms a group. This allows topology to distinguish spaces by their whole structure. There's some examples in the book, particularly in section 1. Okay, so here we go. For example, there we have a circle. So circle 1 has pi log 1 times s equals zeta, because loops can wind around infinitely many times. A sphere is s squared and has so pi log 1 times s squared equals 0, since every loop can shrink to a point. Key topics here is homotopy, Van Kempen's theorem, covering spaces, deck transformations, and classification of surfaces. Hatcher here uses geometric intuition heavily, especially through diagrams and explicit constructions. Let me see if I can pull up a good example of said. Here. Homology section here. Like this. So instead of studying loops alone, homology studies connected components, tunnels, cavities, and higher dimensional voids. The main construction is to break a space into cells, form chain groups, define boundary maps, and compute cycles modulo boundaries. This produces homology groups h log n times x. So intuition, as mentioned earlier, so Hatcher describes this as so h log 0 is connected components, h log 1 is loops and tunnels, h log 2 is cavities and shells, and anything higher than that is a higher dimensional whole. The central ideas here are cyclical homology, singular homology, exact sequences, Mayer-Vaitoris sequence, excision, and cellular homology. One of Hatcher's strengths is showing how abstract algebraic machinery emerges naturally from geometric intuition. So the major theorems here are homotopy invariance, long exact sequence of a pair, excision theorem, and degree theory. This section builds the computational backbone of algebraic topology. Now 3 is cohomology. and this is a refined homology and introduces additional algebraic structures. Instead of chains, cohomology studies the functions on chains. So, for example, it would be h to the power of n times x. And the major breakthrough is that cohomology forms a ring via the cut product. So this is a very long equation. Let me see if I can find it in the book. If not, I have it in my notes. Where it looks something like this. And so this captures how wholes interact with one another. Some important topics here are the universal coefficient theorem, cut products, Cunniff theorem, and Poincare duality. So why this matters is that cohomology often distinguishes spaces that ordinary homology cannot. It also becomes foundational for different geometry, algebraic geometry, gauge theory, and modern physics. So next is homotopy theory, and this is the final section that moves deeper towards more abstract topology. So homotopy theory studies spaces up to continuous deformation and introduces higher dimensional analogs of the fundamental group. For example, it would be pi log n times x. So major topics here are fibrations, CW complexes, spectra, stable homotopy, and obstruction theory. This, what we're moving into now, is like the most conceptually difficult part of the entire textbook. And the central theme becomes that spaces can often be understood through the algebraic behavior of maps between them. And Alan Hatcher, develops tools that lead into modern research areas such as stable homotopy theory, characteristic classes, spectral sequences, and algebraic K theory. And so one of the reasons this book is really famous is because of Hatcher's style. It's highly geometric, intuitive, proof-oriented, filled with diagrams, and less formalistic than older texts. And for example, I'm back on the homotopy theory section of the book, and you can see like there's a ton of diagrams and examples showing this whole nonsense. Anyways, the book is demanding mathematically, but unusually readable for graduate level topology. Now, this we're going to move towards the philosophical idea behind this book, believe it or not. So the entire book revolves around a single principle. It's that convert topology into algebra without losing geometric meaning. So topology asks, what is a space? What kinds of holes does it contain, and how can space deform? And algebraic topology answers by assigning groups, rings, chain complexes, and algebraic invariants. That remain unchanged under continuous deformation. So finally, why this book matters is because Hatcher's book became standard because it modernized algebraic topology, unified geometry with algebra, and made difficult concepts visual. And it's foundational for many fields such as obviously geometry and topology, mathematical physics, algebraic geometry, manifold, and category theory. And so for many mathematicians, it is the first serious encounter with modern abstract mathematics beyond calculus and linear algebra.